All right, today we're going to finish chapter 19 and go through some of chapter 20. Let's see. Okay, past that. All right, so here is where we left off. All right, so in the book, for whatever reason, they like to use the log log instead of the ln. And so they have multiplied everything by 2.303 and changed it to log. I will never use that system. I will always use these reactions. Of course, if you want to multiply that by 2.303 and use log log, that will also give you the same answer. If you like this one number divided by n, the one number that I would use is when you take your 8.314, your 298, multiply those together, and then divide by your 9.65 times 10 to the fourth. And that would give you a different number here, and that difference is a difference of 2.303. You just divide that number by 2.303. Again, I don't use that either. I put in the numbers every time. Here's just a bunch of different formulas to get to different variables. All right, so here is a question. We have a cell that is a zinc and a copper cell, so you should write out the reactions. You got your zinc going to zinc plus 2 electrons, and you have your copper plus 2 electrons going to copper. And when you add those up, they've done that for you, and here is your overall reaction. All right, so from writing this half reaction for oxidation and reduction, we see that our number of moles of electrons is 2. We have 2 electrons lost, we have 2 electrons gained. So that gives us our N value of 2. All right, when we're looking for the Kc, or when we do our equation where we have our delta G is equal to negative NFE, not cell, and we also have that delta G is equal to negative RT ln KEQ. All right, it's not asking for KEQ, it's asking for KC, and that is because they are the same. Because if we do the setup for Kc, it is the concentration of the products, zinc plus 2, divided by the concentration of reactants, which is copper plus 2. And since everything that's in the KEQ is a concentration, then that means that it is a Kc. So Kc just has all of the things that are in your equilibrium to be in concentration in molarity. If everything was a gas, you would have Kp. All right, if you had a mixture of gases and concentrations, then it would just stay labeled as KEQ. All right, so we are looking for our KEQ. So all we need is our N. We've got that. It's 2. We need our F. That's a constant. E naught cell. This is the standard cell potential. They did not have to give us the 1.10 volts because we could have looked them up in table 19.1. And we would have found that our zinc number would have given us 0.76 volts and our copper number would have given us 0.34 volts. And when we added those up, we would have gotten our 1.10 volts. All right, we didn't have to do that because they gave us that answer of 1.10 volts. All right, so then we have our E cell. R is the 8.314. Temperature is 298. So we just have the one unknown, and that is the KEQ. All right, so when you put in all your numbers, okay, if this delta G is equal to this and that delta G, okay, then you have negative NFE naught is equal to negative RT ln KEQ. So you got negative 2 moles of electrons. You've got Faraday's constant, 9.65 times 10 to the fourth coulombs per mole of electrons. You've got your E naught cell, 1.10 volts, and that's equal to negative 8.314 joules per mole Kelvin, 298 Kelvin, and ln of KEQ. So we divide both sides by negative 8.314. Divide both sides by negative 8.314. So that and the negative is gone. Divide both sides by 298. Divide both sides by 298. That's gone. And then you have a number is equal to the ln of KEQ. All right, so then you push your e to the x button, and then you get your value for your KEQ. And that is 1.6 times 10 to the minus 37. No, positive 37. All right, so I had a positive E value, so I know that it is delta G is equal to negative NFE naught cell. And so anytime your E value is positive, F is a positive number, moles always is positive, you have a negative delta G. So I know this reaction is spontaneous because our E value is positive and therefore the delta G is negative. All right, and so once you know it's spontaneous, you know you're going to have a large KEQ value. And when you push the buttons, you get 1.6 times 10 to the positive 37, very large number. All right, so again, they're doing it as the LOG, so they have log is equal to 37.2. We had ln is equal to a different number, but it doesn't matter. At the end, you get the same answer, 1.6 times 10 to the 37. I will always use the ln. I will not use the log. All right, so now we're going to do the Nernst equation. All right, so this is when we are not at equilibrium. All right, so we're going to have a Q value, not a K value. And so again, your setup for Q is the same as your setup for K. So Q and K, so we can call it Q EQ is equal to K EQ is equal to your concentration of your products. Or if we have gases, pressure of your products divided by concentration of reactants. Or if we have gases, pressure of reactants. All right, so it's the exact same setup. It just is KEQ is at equilibrium. And QEQ is not at equilibrium. Usually the initial state. All right, and so we have our E cell. So this is what we are going to, if you made something and you hooked up your voltmeter, that's what it reads. If you have your E naught cell, that is from table 19.1. So you always calculate your E naught cell from table 19.1. And that's when your concentrations are all 1 molar, and that's when all your gases are at 1 atmosphere of pressure. If you have different concentrations or different pressures of gases, then you're not an E naught cell. Then you are an E cell, and you have to calculate it by finding your Q value by taking the concentration of products over reactants. All right, and so you have question using the Nernst equation, and here it is. All right, so we have our reaction. We should always write the reaction, the cell reaction. Zinc is going to zinc plus 2 electrons. And that, of course, was our 0.76 volts. We don't need to do that because they give us the answer, but we're going to do it because the answer is usually not given. Cu plus 2 electrons goes to Cu. And that E value from table 19.1 is 0.34 volts. And so when you add these up, it's important to see that you have 2 electrons gained and 2 electrons lost. So we now know our N value is 2. So we have our copper plus 2 plus our zinc going to zinc plus 2 plus copper. All right, so now we have initial concentrations that are not 1 molar. And so we are going to find the Q value. And so the setup for Q, I'll put Q, EQ. It's going to be QC because they're all concentrations. But the setup is the same whether your Q or your K. And that is the concentration of products, zinc plus 2. Remember, we never put liquids or solids in an expression for KEQ or QEQ. Divided by your concentration of your copper. All right, and so it wants the cell potential. All right, so not the standard cell potential. The standard cell potential, again, that's from table 19.1. Table 19.1. That's where we get the 0.76. That's where we get the 0.34. We add it up. We get the 1.10 volt. In this case, they gave us that answer, but most cases will not. That's how you find the 1.10 volt. So we want to know what our cell potential is. So we're looking for E cell. We know the E naught cell. That's from table 19.1. That is 1.10 volts. Minus your RT over your NF ln of Q. Oh, I'm going to put EQ, QEQ, or you could put QC. All right, that's a Q, EQ, doesn't matter. You just put Q. All right, so E cell, that's what we're looking for. We have the E naught cell, that is 1.10 volt. We have R, that is 8.314 joules per mole Kelvin. We have the temperature, it is 298 Kelvin. And we wrote out the reaction. We saw 2 electrons gained, 2 electrons lost, 2 moles of electrons. And Faraday's constant, which is 9.65 times 10 to the 4th coulombs per mole of electron. And that is then the ln of Q. So now we have to calculate our Q value. So what is the Q value? It's right here. It is the concentration of zinc divided by the concentration of copper. So your Q value is the concentration of zinc plus 2 divided by the concentration of copper plus 2. And those are given. The zinc plus 2 concentration is 1 times 10 to the minus 5. The copper concentration is 0.1. And so when you take that and divide it by the 0.1, you get 1.00 times 10 to the minus 4. All right, so that is your Q value. All right, so then you push the buttons, you get E cell is equal to 1.10 volts minus, and when you push all of the buttons here, you get a negative 0.12 volts. Now, where do volts come from? Volts aren't anywhere here. You've got no units. When you take the ln or an log of a number, there are no units. Moles of electrons cancel moles of electrons. Kelvin cancels Kelvin. You end up with a joule per coulomb. And remember that a coulomb times a volt is equal to a joule. And so a joule divided by a coulomb is equal to a volt. So that's where volts comes from here. So you have to remember that your coulomb times a volt is a joule. That's just units. All right, and so your E cell is equal to 1.22 volts. All right, so you have a higher voltage than the standard cell. You will always get a higher voltage than the standard cell when your Q value is less than 1. So when the Q value is less than 1, this is going to give you a negative number. This is negative 9 point something. Remember exactly. All right. So that is a negative number. All of these numbers are positive. All right, so you're going to have a negative, and then you're going to have another negative. So it's a negative of a negative. You're adding, you're going to have a higher voltage. So anytime your Q value is less than 1, you're going to have a higher voltage. All right, some of these problems may be to determine your H, or it may not say H plus, it's going to say calculate pH. When you are calculating pH, what you're going to have as part of your Q value is going to be some H plus concentration. And so you're going to solve for Q, and then you're going to have all of the concentrations except for the H plus concentration. Solve for that H plus concentration, put it into your pH is equal to the negative log of H plus, and then you would have your pH of that solution. So if they're asking for pH, you got to know that you're finding the H plus from the Q value and then plugging it into your pH equation. All right, so here's another cell reaction. We have iron solid going to iron plus 2. Plus 2 electrons. I think that is 0.41 volts, if I remember correctly. And then we got our copper plus 2 electrons goes to copper. And the E value for that is equal to 0.34 volts. And so when you add those up, you get your overall reaction of copper plus 2 plus iron solid metal goes to copper solid metal and iron plus 2 with an E value of 0.75 volts. All right, so you have a positive E value, you have a spontaneous reaction, a negative delta G, and that is just the question for A. All right, because we know that delta G is equal to negative NFE naught cell. All right, and so when that is a positive number for your E naught cell, then that is going to be a negative delta G. All right, so that is a negative delta G, and this is spontaneous. All right, so now it says to change the concentrations. Again, when you're doing your E naught cell from table 19.1, that again is when your concentration of iron is 1 molar, your concentration of copper plus 2 is 1. All right, and now it's going to be change the concentrations from their standard values, which is 1 molar, in such a way that your E cell is reduced. So we want a lower voltage, all right? So remember when our Q EQ, when it was less than 1, as we had last time, 1 times 10 to the minus 4, when it was less than 1, we got an increase in our E cell. All right, so this time our QEQ is got to be greater than 1, and then we will get a decrease in our E cell. All right, so if we write our Q value, our expression, that is the Fe plus 2 concentration over the Cu plus 2 concentration. And for our E cell to be lower than our E naught cell, we need to have a Q value that is greater than 1. And so we need to have a Fe concentration has to be greater than your Cu plus 2 concentration. All right. We have to have a number when we do that division to be greater than 1. So if your numerator is larger than your denominator, then you're going to have a positive value in that division. So any number you pick, if you want to pick whatever, 2 molar here and for your Fe plus 2 and 0.5 molar for your Cu plus 2, you can do a quick calculation. You put in the 2, you put in your 0.5, your Q value is 4. All right, so that is greater than 1. And so that would give you a decrease in your E cell value. So here they pick a higher number and they use 1.1, and the lower number they use 0.5, whatever it doesn't, well, that's what I picked too. So then that Q value, products over reactants, would have been a 2.2. Any Q value that's greater than 1 is going to give you a decrease in your E cell. All right, there's a lot of batteries that we are not going to be tested over. Just a bunch of different types of batteries that are all voltaic cells. Regular AA's, AAA's, C, D batteries have the 1.5 volts. The lead storage cell is your car battery. Is, well, depends. They make different kinds of car batteries now, but back in the day, they were all a lead storage cell, which gave 2 volts. So here's your anode, here's your cathode, and you would have it in an aqueous sulfuric acid solution. And that was usually about a 6 molar. Battery acid is about 6 molar sulfuric acid. And you would have to then fill your battery with water occasionally if it went lower. And there were 6 of these cells because, of course, your battery in your car is a 12-volt battery. This is a little over 2 volts for each one of these lead cells, and so they would put 6 of those in series to give you a 12-volt battery. The newer batteries, you don't add water to them, so they are maintenance-free, and they use calcium metal, which resists the decomposition of water. So in a battery, you're losing a lot of water because you can electrolyze the water into hydrogen and oxygen, and then if you have a spark, you can have batteries blow up and all kinds of fun stuff. But there's not going to be any questions on the batteries. So here's your nickel cadmium rechargeable batteries. You got your lithium, you got your fuel cell. So your fuel cell is where you take your water and you convert it into hydrogen and oxygen. Okay. And we need to get to electrolytic cells. All right, good. All right, so all those were voltaic cells, which means they generated a voltage. All right, so you put batteries in something and now it is running. All right, your electrolytic cell is something that is non-spontaneous, and you will need an external energy source in order to make the reaction go. So you have a non-spontaneous, so an electrolytic cell, your E value is going to be negative, and your delta G is going to be positive. So your E naught cell is negative, and your delta G is positive. These are non-spontaneous reaction. All right, so the process of producing a chemical change in an electrolytic cell, that is called electrolysis. So many different commercial products use electrolysis. The way that we will get our sodium metal is we will do an electrolysis of a molten salt, and that salt would be sodium chloride. All right, so we're going to do the electrolysis of sodium chloride, and that would then separate that sodium chloride into sodium and chlorine gas. All right, so what you do is you have it at a very high temperature. You have liquid sodium chloride or molten sodium chloride, and it goes through electrolysis, and the sodium becomes sodium liquid, which then is cooled. It is very high temperature to melt NaCl. When it's cooled, you have sodium metal, and you also are producing chlorine gas. So anyway, there's a picture of your sodium chloride, molten sodium chloride, converting into sodium liquid because of the high temperature and chlorine gas. And then again, you cool it and you get your lithium solid metal. Aqueous electrolysis, you have two reactions that have water in them. You have the reduction half reaction where your water is reduced to hydrogen gas and hydroxide. You also have the oxidation half reaction where your water is converted to oxygen and acid. All right, so there's two possible reactions when you have your water. You can oxidize it into oxygen, you can reduce it into hydrogen gas. All right. Electroplating of metals, another very important process that we do in most examples include zinc, and it's called electrogalvanizing. All right, so we have galvanized metal. Anytime you have some galvanized steel, galvanized whatever, that means it is coated with zinc. And so we coat it with zinc because that would prevent rusting. All right, so zinc does not rust. Unfortunately, zinc does react with acid. So if you leave it out in the rain, you have acid rain, it's going to dissolve that zinc right off of the surface, and then it'll start to rust. All right, stoichiometry of electrolysis. All right, so we got Faraday's constant. All right, and so we have moles of electrons. So we are going to be calculating moles of electrons from a mass of a metal being deposited. All right, so you have your two equations that are going to be important for electrolysis, and that is Q is equal to IT and Q is equal to NF. So, of course, IT is equal to NF. I will combine them. The book likes to solve them separate. All right, so what you need to know is you need to know that I is your current, and that is in amps. T is time, that is a lowercase t, that is time. And the units have to be seconds because Q is charge, and that is in coulombs. And so an amp times a second is a coulomb. All right, and so we already know the N and the F. N is moles of electrons. And F is Faraday's constant, 9.65 times 10 to the fourth coulombs per mole of electrons. All right, so here they have the electric charge. Of course, they're saying Q, and the electric current, that is I, and time. All right, so the Q has to be, Q is going to always be in coulombs, I is always going to be in amps, time will always be in seconds because an amp times a second is a coulomb. All right, so we have a constant current that was passed for 5 hours. We convert that to seconds. That needs to go to seconds. And 404 milligrams of copper metal was deposited. We have to convert that to moles of electrons. What was the current? All right, so you have your Q is equal to IT. You've got your Q is equal to NF. And so IT is equal to NF. All right, so there are only three variables. F is not a variable. F is a constant. We have three variables. All right, you have to be given two of them, and you're going to solve for the other. All right, so what we're given is a time that we have to convert to seconds. What we are given is a mass of copper that we will convert to moles of copper, but we don't want moles of copper. N is not moles of anything. N is moles of electrons. So once we have our moles of copper, we will have to use the mole ratio that we have 2 moles of electrons for every 1 mole of copper. All right, so we will take our 404, and then instead of milli, I'm going to write times 10 to the minus 3 grams, or you could have just written 0.404 grams. And then I have to divide by the molar mass of copper, which is 63.6 grams per mole. Now we have moles of copper, but we don't want moles of copper. N in this equation is specific. It is moles of electrons. And so from our balanced half reaction with copper, we see that 1 mole of copper is produced when 2 moles of electrons react. All right, and so now we have the correct moles of electrons. And then we convert our 5 hours. All right, so there's 60 minutes in an hour. And there are 60 seconds in a minute. And so we multiply 5 by 60 and then 60 again. And now we have our time in seconds. All right, so now we just plug our moles in here. F is a constant. Plug that number in. Put in our time in seconds. Divide both sides by the time in seconds. And we will then calculate the current. All right, so again, you take your grams of copper. All right, so a milligram is 10 to the minus 3, so 0.404 grams of copper, divide by the molar mass. Then use the mole ratio, get the moles of electrons. Then you have your Faraday's constant. And so here is your Q in coulombs, and this is your N moles of electrons, and this is your F. So we're using first the Q is equal to NF. The book likes to give intermediate answers, and then they put that into Q is equal to IT. And so they're going to take this Q value and divide by T. So divide both sides by T, and then you have your current. And so you have, when you multiply the 5 by 60 and 60 again, you get 1.80 times 10 to the 4 seconds. All right, so then you take your coulombs divided by your seconds, and a coulomb divided by a second is an amp. And so that is 0.0681 amps is your current. All right, so they did Q is equal to NF, and then they did Q is equal to IT. I put them together and do it all in one step. It makes no difference. The answer is the same, 0.0681 amps. All right, so that time we were given a mass and we were asked for a current. This time we're given a current and a time, and we're asked for the mass. All right, so again, we're going to use Q is equal to IT and Q is equal to NF. All right, I always put them together. IT is equal to NF. Current is 8.52 milliamps. And so I have 8.52 times 10 to the minus 3 amps. I have 10 minutes, and I know there are 60 seconds in a minute. So I have 600 seconds. So I have my current, I have my time, I have Faraday's constant, 9.65 times 10 to the 4th. All right, so I have 3 of the 4, I have 2 of the 3 variables. F is not a variable, it is a constant. So I just plug in my numbers. For my current, I have 8.52 times 10 to the minus 3 amps. Units are very important. It has to be in amps for your current. It has to be in seconds for your time. 600 seconds. That is equal to moles of electrons times Faraday's constant, 9.65, times 10 to the fourth. All right, so then you just divide both sides by 9.65 times 10 to the fourth, and then you have moles of electrons. And that, if you divide both sides by 9.65 times 10 to the fourth, you get 5.3 times 10 to the minus 5, 5.30. Moles of electrons. All right, so then you have your balanced chemical half reaction, and you see that when 2 moles of electrons are formed, we only form 1 mole of iodine. So 1 mole I2 per 2 moles of electrons. All right, so then we divide that by 2, and we get our 2.65 times 10 to the minus 5. That's moles of I2. All right, so then you look up the molar mass of iodine. It is 127, but you have I2 for iodine, and so that is 254. So now we multiply that by 254 grams per mole, 254 grams per mole. So multiply by 254, and we get 0.00673 grams, or 6.73 milligrams of iodine. All right, so again, you could be given the mass, then you would have to convert that to moles, always moles of electrons, and then you could figure out your amps, like the first problem. You can be given an amps and a time, and as for the grams, how much was deposited, you could be given the amount deposited and the amps and be asked how long did it take. Again, you have 3 variables in your IT is equal to NF. 2 of them must be given. F is always given. It is a constant. All right, so you have to be given 2 of the others. So far, we've been given the first time we were given a mass, so we could get moles of electrons. We were given a time. This time, we were given a current, I, and a time, and so we solved for N. All right, so the other choice is you're going to be given time, or your current and your moles, and you will solve for time. All right, so that is the end of chapter 19. So now we're going to start chapter 20. Which is nuclear chemistry, which is not going to be balancing reactions by having the same number of atoms on each side of the equation. We're going to balance the protons and neutrons on each side of this reaction. All right, so in chemical reactions, we are using the electrons. So if you remember your atoms, you got your protons and you got your neutrons in the nucleus, and then surrounding your nucleus, you have your electrons. All right, and so when your electrons were transferred, we had an ionic bond. When your electrons were shared, we had a covalent bond. All right, and so your chemical reactions were all about breaking bonds, making bonds, and that's all about the electrons. In nuclear reactions, we're going to talk about the nucleus, which is your protons and your neutrons. Here, we will make different elements. In a chemical reaction, you have a conservation of mass, which is not really a conservation of mass, but the mass that is changed is very small, and so we call it a conservation of mass. Nuclear reactions, huge mass differences, not a conservation of mass. Chemical reactions, you balance the atoms on both sides. Nuclear reactions, you balance the protons and neutrons on both sides. All right, so we have radioactive decay. We have things that are radioactive. That means that they are spontaneously giving off radiation. All right, so you have a spontaneous reaction. So, of course, your delta G is negative. All right, so they are decaying, giving off a particle. A nuclear bombardment reaction, that's when we take a nucleus and we hit it with a particle, and then another nucleus is formed and usually kicks out another particle. All right, so some reactions will just go, they are radioactive. Some will require a bombardment reaction to get them to go, and sometimes get them to do what you want them to do. All right, we're going to talk about a lot of different particles. We're going to be talking about the beta particle. We're going to be talking about the gamma particle. We're going to be talking about the alpha particle. You will have to memorize all these particles, knowing their number of protons and neutrons in their nucleus. All right, so we're going to use the nuclide symbols. Back in chapter, I don't remember, 3, maybe 2, I'm not sure, where we did the nuclide symbols. So here is a nuclide symbol. So remember, your top number, in this case, the 238, that is your protons plus your neutrons. The bottom number, that is your protons. That is also your atomic number. And that's how you know what element it is. So if you look at a periodic table and you find element number 92, that has a symbol of U. If you go to the periodic table and you look for the element that has atomic number 90, that symbol is TH. You don't have to know uranium and thorium. You just have to know the number, look up the periodic table, and then you have the symbol. Again, here you have 2 as your atomic number. Look at the periodic table. That, of course, is helium. When you're balancing a nuclear reaction, obviously we're not balancing the atoms. We have 1 uranium on this side and no uraniums on the other side. What we're balancing is the number of protons and neutrons. They have to be the same on both sides of your nuclear reaction. All right, so uranium has 238, your thorium has 234, your helium has 4. So you see that you have 238 equals 238. On bottom, you have your protons. The protons have to be the same on the left and right. All right, your neutrons have to be the same on the left and right. So your protons here is 92. All right, so 92 is equal to 90 plus 2. So that's it. You have 92 here, and that's equal to the 90 on bottom there plus the 2 on the bottom there. You've got 92 protons on both sides. So to balance a nuclear reaction, it's simply the numbers on top on both sides of the equation have to be the same, and the numbers on bottom have to be the same number of protons and neutrons on both sides. We're going to talk about radioactive decay. Some we already did. We showed alpha is not on here. I don't know why, but anyway, alpha. So an alpha particle is a helium 4-2. So that is something you can make a flashcard, whatever. You have to know that an alpha particle is a helium 4-2 particle. A proton is a 1-1 hydrogen, or you could put 1-1p for proton. Most people will put 1-1 hydrogen, but either one is fine. A neutron has 1 neutron, but no protons. 10 is the number for a neutron. You need to know the neutron. An electron, well, there's 0 protons and 0 neutrons, but a charge of -1. And so it is a -1 charge. So a 0 minus 1 is an electron. An electron is also called a beta particle. And if it says beta particle and you write E, I'm not going to count that wrong. The 0 minus 1, that is the key. All right. And so your beta is a fancy little B here. All right. So then a new one would be a positron. A positron is a positive electron. That means that it is not a proton or a neutron. It is a positive electron. And so this is where your number on top is the number of protons and neutrons. The number on bottom is not the number of protons. So this one is weird. You can't have a negative proton either. There's no such thing as having a negative proton. All right, so you have a negative charge with no mass for an electron. You have a positive charge with no mass for a positron. And so same thing here. It could be written as an E01 or a beta 01. A gamma is simply pure energy. So that is a 0, 0. That is just releasing energy. Very, very high. If you remember your electromagnetic spectrum, your gamma is the highest energy. That is a lot of energy being released. So you need to know the names and you need to know the particle with the numbers that go with it so you can balance your nuclear reactions. All right, so then they just explain a few things. Positron is a positive electron. Gamma is pure energy. All right, so here, write a nuclear equation for the radioactive decay of radium. All right, so radium-226 is going to decay. All right, and it's going to give off a radon-222. And one alpha particle. So that's where you need to know what an alpha particle is. And so that is a 4,2 helium. All right, and so you look at the periodic table and you get your numbers. Ra is 88. Rn is 86. And then you check to make sure that your numbers are the same. And they are. You got 226 for the top number, which is equal to 222 plus 4. Yes, 226 now is 226. You got 88 on the left. You got an 86 plus a 2. You got 88 on the right. And so you have a balanced nuclear reaction. If you don't know an alpha particle is a helium-42, you cannot get this right. You have to make sure you know the particles and the correct numbers that go with them. Protons and neutrons, things inside of the nucleus, are called nucleons. All right, so your protons and your neutrons, these are called nucleons, things that are in the nucleus. All right, so the total number of nucleons is conserved. Again, you have the same number of protons and neutrons on both sides of a nuclear reaction. All right, technetium, 99. Look at the periodic table, you find that is element number 43. All right, so you have isotope of technetium. Each nucleus decays by emitting a beta particle. Again, if you don't know the numbers for a beta particle, you will not be able to get this right. So you have to know that a beta particle is the same as an electron, which is 0 and -1. All right, so whether you put beta or whether you put E, that doesn't matter. If it says beta, I'm always going to put the beta symbol. Again, the E, 0 -1, is going to give you the exact same answer. So the answer is, what's the product nucleus? All right, so we see that the top number has to be the same. 99 is equal to 0 plus, of course, 99. So 99 plus 0 is equal to 99. Here's the one where people get it wrong. You're adding a negative 1. So you have to have a 44 plus a negative 1 to give you 43. And so then you look up element number 44, and you find that element number 44 is ruthenium. All right, and so you have your number. So this is, you're given that. You have to know that a beta particle is a 0 minus 1, whether you call it E or beta, that doesn't matter. All right, and so you have to be able to get your other number. So you have to see that 0 plus 99 is 99. And 44 minus 1 is 43. And then 44 is your atomic number. So you just go to the periodic table and you see Ru is the symbol for element number 44. All right, so some nuclei are more radioactive than others. All right, so we look at the stability of our nuclides that we have. And just like in our chemical reactions, we have our noble gases that have everything wants to have the electron configuration of a noble gas. We are also going to have a model for the nucleus. All right, and we call those magic numbers. Not sure why they call them magic numbers, but whatever. They call them magic numbers, numbers of protons and neutrons that are very stable, just like our noble gases. So helium is 2, neon is 10, argon is 18. Okay, so those are your very stable electron configurations. That's your very stable number of electrons. All right, so for protons and neutrons, I guess, or neutrons, if you have 2, 8, 20, 28, 52, or 82, then that is the magic number of protons or neutrons, and you would predict those things to be stable. All right, so if they have the magic number, then they are going to be stable, not radioactive. All right, so you would predict it at least to be stable. All right, neutrons has another number. For neutrons, you can add a 126. For protons, you can add another number, 114. I'm not going to use those on the test. I'm going to use the ones where they are the same. The 2, the 8, the 20, the 28, the 50, and the 82. So you should be aware of the magic numbers for your protons or your neutrons. If you have that number, you would predict that to be stable. All right, and this one is a probability. So if you have a nuclide that has an even number of protons and an even number of neutrons, you would predict that to be stable. There are 157 stable isotopes. That is a lot of stable isotopes here. So if you have an even number and an even number, you would predict that to be a stable compound. If you got one even and one odd, you got 52 that was stable this way, 50 that way. Okay, so it may or may not be stable if it's even or odd. If they are both odd, you would definitely predict that to be unstable. All right, so that is just a prediction. Of course, they're not all unstable. There are 5 that are stable. So you would then predict anything that has 2 odd numbers to be unstable. It is very rare to be stable. Again, here, even, you would predict this to be stable. All right, so your even and your odd over here, you would predict it to be stable if that even number was one of your magic numbers. No stable nuclei exist for atomic number greater than 83. If your atomic number is greater than 83, you are unstable. So if your atomic number is greater than, you are unstable, which means when you are unstable, that means you are emitting radiation. That means that you are radioactive. So unstable means radioactive in this chapter where we are talking about the radioactivity of different nuclei. If it's unstable, then it is releasing particles. It is radioactive. All right, so it's very common to give a pair of nuclide symbols and say which one do you predict to be stable, which one do you predict to be radioactive. And a good thing to do here is get your protons and your neutrons. Get your protons and your neutrons. All right, so you got 84, you've got 83. All right, to get your neutrons, you simply subtract. That is 124, because 84 plus 124 is 208. Do subtraction here, you got 126. All right, so that could mislead you. What you need to see here is that this number is greater than 83. This number is not greater than 83. This number is equal to 83. And so when your Z is greater than 83, not equal to, then you are radioactive. And so since this is greater than 83, this one is radioactive. And so then you would predict the other one to be stable. So remember, radioactive means unstable, so the other one would be stable. All right, so down here, they're both 31, neither one greater than 83. So you have your protons, 31 here, protons, 31 here, that's the same. Neutrons here, you've got 40. Neutrons here, you've got 45. And so what you see here are two odd numbers. 31 is an odd number. 45 is an odd number. The chances of that being stable are very, 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 very slim. And so you predict this one to be unstable, radioactive. And the other side would be stable. And so that again is a prediction that is not 100% sure. There are 5 that have an odd and an odd that are stable. But again, the majority of them are unstable, which is radioactive. All right, and so they ask for both questions. So they say which of these is radioactive and which is stable. All right, so radioactive is unstable and the other one is stable. It's unstable because it is going to emit some particle. All right, so and then also this one, also the 126 was a magic number for the neutrons. That was not necessary to know because one is greater than 83 and it is radioactive. And here, yes. Right. The other one were both out. All right. All right, 6 common types of radioactive decay. So it's radioactive, it's unstable. What is going to happen? Well, here are 6 common types of radioactive decay. The first one we've already seen, it is the alpha emission. Again, remember, this is very simple, unless, of course, you don't know alpha is helium-4 then it is impossible. So we already saw this reaction here where you have your 226, which is equal to 222 plus 4. You got your 88, which is equal to 86 plus 2. All right, so alpha emission is a very common type of radioactive decay. Beta emission, also a very common radioactive decay. So you have, and so you can write it as a 0, -1e or 0, -1 with a beta symbol. All right, so you have your carbon-14, 6. That's your nuclide symbol. That is going to do a beta emission. And so you would have to be able to write your 0 and your -1. So the top number, very simple, because 0 plus 14 is 14. The bottom number, when it's negative, people mess that up. Be very careful. This is easy. Don't make a silly mistake because your 7 minus 1 is 6. 5 minus 1 is 4. All right, so make sure you know that you're putting a 7 minus 1 to give you the 6. Neutron can undergo beta emission and emit also a proton. Right? So if it says a neutron, you have to know that that is a 10N. And then a beta emission, you have to know that's 0 minus 1. All right, so you know this and you know this. All right, and you are going to get the numbers for the other. All right, and so you have a 0 on this side and 1 on this side, so that has to be a 1. You got a 0 on this side and a negative 1 on this side. This has to be a 1. So again, whether you put P here or you put H, I would normally put H 1 and 1. And when it's a beta emission, I would have a 0 minus 1 with a beta. That is the same thing. So you can write a 1, 1P plus a 0 minus 1E, or you can write a 1, 1H plus a 0 minus 1 beta. Or you can write the P with the beta, or you can write the H with the electron. So it doesn't matter if you put 1, 1H or 1, 1P. It doesn't matter if you put 0 minus 1E or 0 minus 1 beta. Again, the numbers are what's important. You have to have the 1 and the 1. You have to have the 0 and the minus 1. A positron emission. Again, a positron emission is a positive electron. So that is a 0, 1. Right? And whether you write it as a 0, 1E or a 0, 1 beta, then it is the same. It doesn't matter. It's the same numbers. All right. So what you'll find that a proton will undergo a positron emission. All right. So your proton number is 1, 1. Your positron is 0, 1. So you got to get the other number. The other number is a 1 on the top. The other one is a 0 on the bottom. And you have to know that a 1, 0 is a neutron. Technetium also undergoes positron emission. All right, so it would tell you that it's technetium 95. All right, so that is 95 and 43, and it tells you that it undergoes a positron emission. So that is a 0, 1. So you have to get the number on top and bottom. Again, there's a 0 on the top, so it's simply the 95. On bottom, 42 plus 1 is 43. So you go to element number 42, which is MO, to balance that nuclear reaction. Electron capture. All right, so I didn't emphasize that a lot. Emission, emits, that's a product. Anytime it says emission, it is a product. It is giving something off. A capture, that means it is going to be a reactant. All right, so when you're doing a capture, that means it is a reactant. When you're doing an emission, it is giving it off. It is a product. All right, so if a proton undergoes electron capture, so now you've got a proton plus an electron, and that's going to yield, well, on top, you got a 1 plus a 0, that's a 1. You got a 1 plus a negative 1, which is a 0, and you have to know that a 1, 0 is a neutron. All right, if you take potassium 40 and it undergoes electron capture, so you would write 40 and then 19 because that's the atomic number for potassium. And then your electron is a 0 minus 1E. You could put beta here, but when it says electron capture, I'm going to put E. All right, and so you have your 40 plus your 0, that's 40. You got your 19 plus your minus 1, that's 18. Atomic number 18, that's argon. To balance the reaction is very simple, but you have to know the particles and the correct numbers that go with the particle. Nothing is easier than a gamma emission because it is simply a 0, 0. Now, what you're putting here is a technetium, and it's a little m. What that m means is that it is unstable. It is a metastable nucleus, which means it is unstable, which means it is high in energy. and it wants to release some of that energy. And it does that by emitting a gamma particle. All right, and so that is simply a 0, 0. So you have 9943, you end up with 9943. So they put a little M here to indicate that, yes, something is happening. What's happening is your technetium is at a excited state, a high energy state. It is releasing energy and coming down to a lower energy state. All right, fission. So when you have your fission reactions, and this is what we do in our nuclear power plants, you will bombard a nucleus with a neutron, and you will break it into two other smaller nuclei. And when you're doing fission, it requires a neutron to start it, and you always release neutrons. It's a chain reaction. And so then those 4 neutrons can then bombard 4 more uraniums. All right, they've included the neutron in here already. It should be uranium-235 92 plus a neutron. All right, and so that's what is actually going on here. You got your uranium-235, the fuel for nuclear fission in nuclear power plants, and you hit it with a high energy neutron. That neutron goes into the nucleus and forms an unstable uranium-236, which then breaks into 2 particles and emits some number of neutrons. You cannot predict the products. The only product that you can predict is neutrons, but you can't predict how many. All right, so you know that it's going to break into 2 smaller nuclei and you're going to get neutrons. That's the only thing you know. And you have to be given 2 of the 3 products. All right, so if you're given, let's say you're given these 2 and it says how many neutrons are released. All right, so you have to have your number on top and bottom be the same. So we have 235 plus 1, that's 236. So we need 236 on the top here. So we have 136 and we have 96. So we need 4 more. And so you can write for 10N, or of course, you could write that out 4 times. All right. So you can write a coefficient of 4 in front, or if you prefer, write N10 4 times. And so now when you add up your 96, your 136, and your 1, your 1, your 1, your 1, you get 236. When you add up your 39 and your 53, that is your 92. When you add up your 92 and your 0, that is your 92. All right, so you cannot predict the products of fission. 2 of the 3 products have to be given to you. And you can then calculate the 1 missing product. But fission, that is when you split a larger nuclei into smaller nuclei. Did it say 6? Okay, fine. Of course, we're going to do fission, and that's what we do on Earth. Fusion is the sun, the stars, and that's when smaller things come together to form bigger things, and we will talk about that soon. All right, so you have your nice chart here of types of radioactive decay and how to predict them. Yep, okay. So an alpha emission, anything greater than an atomic number of 83, you would predict that to do an alpha emission. So all of your nuclides have an atomic number greater than 83 are radioactive, and that would be predicted to be an alpha emission. Again, it is the usual nuclear condition. It is usually what happens when you have a nuclide that has a higher than 83 protons. A beta emission, all right? So when you emit a beta particle, that is when your N over Z is too large. Okay, so we have No good examples. Okay. Atomic numbers plus 1. All right, so let's look at carbon 14. And let's say that it undergoes, well, let's try this one. Let's do the beta emission. Well, it's obviously not greater than 83. All right, so let's do a beta emission. So that is a 0 and a -1. All right, and so since I said beta, I'm going to write B. All right, and so what would the product be? Well, the product would be 14 on top, and on bottom, a -1 plus a 7, and 7 is nitrogen. All right, so what you have here is an N over Z too large. I'm not sure why they can't just use regular language. Your mass is too large. All right, so if you look at the periodic table and you look at carbon, it says the mass of carbon is 12.01 grams per mole. And now you have a isotope of carbon that has a mass of 14, and that is higher than the periodic table says it should be. All right, and so when you have a high mass isotope, is what I like to call it, this is a high mass isotope, then you're going to do a beta emission because now you look at nitrogen. You have nitrogen on your periodic table, you look up the molar mass, and it is 14.01. And that is going to be a very stable isotope for nitrogen, which is nitrogen 14. So anytime you look at the periodic table and your isotope that you have is a high mass isotope, higher than the molar mass given on your periodic table, it is going to do a beta emission. All right, now the next two are exactly the same. All right, so they are a positron emission and an electron capture. And that's when your mass is too small. All right, so we'll stick with carbon. So let's say we had carbon 11. All right, so it's not a common isotope. If it exists, we can make it if it doesn't. All right, let's just say we had carbon 11. I just picked an isotope of carbon that is less than 12. So now it is a low mass. So now we have 11 here instead of 12. So now our mass is too small. If we do a positron emission, all right, so a positron is a positive electron. So 0 and 1. And so you can put E, you can put B, it doesn't matter. Positron emission is a positive electron. So the number on top is, of course, 11, because 11 plus 0 is 11. And on bottom, it is a 5, and that is boron. And if you look at the molar mass of boron, it is 10 point something. It is very close to 11. All right, and so what that's getting down to is another element that will have the a more correct mass. All right, so when you look at the mass here, it's going to be pretty close to what it is for a boron. All right, so again, if we said that's the same, it's the same product. All right, so our product here is boron 11. If I said, well, instead of doing the positron emission, let's do an electron capture of 11.6. Now you have to know that capture means you're doing a reactant of an electron, so that's a 0 minus 1. And when it says electron, I put E. I wouldn't count it wrong if you put a beta. All right, and so on top, you got 11 plus 0, that is 11. You've got 5 minus 1, you have 6 minus 1, that is a 5. And again, you get a boron 11. And so you get the same product. And the only time you would pick a gamma emission is when something is in an excited state. And so we indicate that by an M. So M, so you have a 99M, again, that is a metastable excited state. Then you would predict a gamma emission. All right, on Monday, we will finish chapter 20.